Okay. So we'll do an example. Let's do carbon dioxide. And we can do the percent composition of either carbon or oxygen. We'll do carbon first. So we want to find the molar mass of the whole compound to start with. So carbon is about 12 and oxygen is about 16, and there are 2 of them. So let's see, that's 32. So that's going to be 44 for the whole thing. So that's the number that goes on the bottom. So since we're going to do the percent composition of carbon, that number would go on the top. So that will be 12 over 44 times 100. So let me pull up a calculator here somewhere. Oh, Cassian, you're awesome. All right, cool, 27.3%. All right, now we're going to do it for oxygen. Yeah, it's not too bad. It's just the part over the whole. So for oxygen, the part is 16 times 2 because there are 2 of them. And that's 32. So it's going to be 32 over 44 times 100. And that's it for that one. Let me pull up a calculator again. Maybe. See if I can find one. There's one. You guys are quick. 72.73. All right. So that is percent composition. And let's see. You should. So in this case, since I only used 2 would be an exact number, so that's infinite significant figures. So carbon had 2 and oxygen had 2, so our answer should be 2. So in this case, it would be like 73% and 27%. Yes, absolutely. You could subtract 27.3 from 100. All right. Does anybody remember what the question was? No? Okay. Chad, you have a question.
Yeah, it was talking about like which of these compounds is 50% oxygen on a mass basis and which is 50% oxygen on a molar basis or something like that.
Oh, okay. Yeah, I can show you that. All right, so let's see. Anybody remember the compounds? By any chance? All right, so, okay, SO2, SO, and S2O. Okay. We like a whole list on multiple choice. Okay. All right, so I'll just go over these and show you how you would find out what the percentage is, and then I'll show you with moles also. Let's see. Okay, and SO3. Okay, so we'll start with SO3. So we've got sulfur and oxygen. What's the molar mass of sulfur? Anybody know the molar mass of sulfur? I don't have a periodic table pulled up. Let's see if I can pull one up. 32.1, that sounds right. We'll just go with 32. You have another question, Chad? Okay. All right, so 16 times 3, 15 times 3 is 45, so it'll be 48. Oh, no, that's okay, Chad. All right, 32 and 48. So the molar mass of SO3 is 80. Yeah. So in this case, looking at mass, we do 80 grams, not 8, 80 grams over, no, that's backwards. We would do 48 grams over 80 grams times 100. And that's going to give us our percentage of oxygen. So you just do the oxygen over the total. All right. And for moles, I would say something like, if you have SO2, that means you have 1 mole of S and 2 moles of O. So that would be 2 over 3. And then if we were to look at, let's see, SO, that would be 50%. It would be 1 mole S, 1 mole O. So it would be, for oxygen, we're going to put the 1 mole over the total, which would be 1 mole plus 1 mole. And so that's going to be 100. So, I mean, that's going to be 50%. Does that make sense? So with the moles, you're just using the subscripts to figure out what the moles are.
Oh.
Yeah, absolutely. So if you're trying to find sulfur, let's say you're trying to find sulfur in this one, it'd be 1 mole of sulfur over 3 moles total times 100. So that'd be like 33% sulfur and 66% oxygen. All right. So let's take a look at how we can use percent composition as a conversion factor. Let's see. I'll put the number of oxygen. Yeah, absolutely. That's correct, Chad. That's a good question. Okay, let me make it a little more clear. Does anybody need a second on this page before I switch to another one? No? Okay. Okay, good. Oh, wait. Somebody, okay, Chad said yes. All right, so I'll give you a second, Chad. Percent composition and mass composition is the same thing. This would be mass composition at the top. The bottom is, actually the bottom starts, yeah, the bottom's here, I guess. Yeah, okay. So this right here is not percent composition so much. Most of the time when they're talking about percent composition, they're talking about mass percent, which would be the mass of one element over the mass of the whole compound.
Oh, okay.
All right. So let's take a look at SO one more time. All right. So I'm looking for the subscripts, and in this case, there are no subscripts. So I know that that means there's 1 sulfur and 1 oxygen. If I have a mole of this compound, Then I have 1 mole of sulfur and 1 mole of oxygen. Total, I have 2 moles total. All right, so if I'm going to do sulfur, that would be 1 mole of sulfur over the 2 moles total times 100, and that'll give you 50%. Okay, cool. All right. All right, let's look at mass percent as a conversion factor. So we're going to look at actually, hang on one second. I might have skipped something. I don't want to skip anything. Okay. All right, so let's say we have something and it is 58.64% chlorine per CCl2F2. All right, and it doesn't tell us anything else. Now, one thing we could do was we could calculate the mass percent of chlorine and that sort of thing. But an easier thing to do would be to say, okay, if it's this much chlorine, then the rest of it would be whatever's not chlorine, and total would be everything, right? So all total, you'd have 100%. You could actually change the percent sign to grams and say that this is out of 100 grams total. So if you had 58 point, well, you also have to convert this to a decimal. So if you had, well, no, not really. You don't have to do that. Okay. 58.64 grams of chlorine out of 100 grams of chlorine. That's the same as 58.64%. Right? Like if I said I had 25 out of 100, that's the same as 25%, right? So if that's the case, and I'm given something like 25% chlorine out of, I don't know, X, Y chlorine, then I would say I had 25 grams of chlorine for every 100 grams of XYCl. Right? So it doesn't really matter what our compound is. The bottom's going to be 100 grams if they start off by giving us a percent. If they don't start off by giving us a percent, we calculate the percent, and then we can use that information. So let's take a look at it like from the beginning. All right, so we've got CCl2F2. All right, so carbon is 12, chlorine is 35.45, is that right? Like 35 and a half. Let me look that up. $35.45, okay. And we're gonna multiply that by 2. And then fluorine, I have no idea what the molar mass of fluorine is, times 2. Anybody know fluorine? 18.99, I'm just gonna go with 19 for that. And so 19 times 2 would be what? 38? What's 35.45 times 2? 70.9? We'll just call that 71, just to be easy. It's probably best when you're doing your math not to, you know what, I won't do that. I'll just do this instead. Okay. 8 and 2 is 10. So that'd be 12. So it'd be 120.9 total. So if we're going to do carbon, that would be 12 out of 120.9 times 100. So what do we get for that? Should be around 10%. Yeah, 9.93. Okay, 9.93%. So if we had 100 grams, and out of that 100 grams, we had 9.93% of it was chlorine, would that be the same thing as 9.93%? Yes. All right. So what I'm doing is I'm making an assumption here. This above that line is how you do percent composition or mass percent. And then below this is where I make an assumption. If I'm not given all that information, and I'm just given that it's 9.93%, then I can say, well, if I assume that I had 100 grams of whatever it is I'm looking at, then 9.93 grams must be whatever this is, right? So if that was chlorine, this would be chlorine. Or if it was oxygen, then that would be oxygen. So these are two different things, above the line and below the line. Below the line is just how I can make the math easy. If I don't know a whole lot about it, then I can just kind of figure that out. All right, so let's go and do a problem. All right. You can kind of see it more as I go through it. So let's say we have this where it's 58.64% chlorine per, well, and the compound is CCl2F2. Then what that's saying is if I had 100 grams of this, then 58.64 grams would be chlorine. Now, if we did the mass percent in this one, we just did it a second ago, and we did it for, what did we do it for, carbon or chlorine?
We did it for carbon.
I think we did it for carbon. Yeah, we did it for carbon. So, because I was like, chlorine, wasn't that 9%? But anyway, so then we could say we have this right here of the compound. All right. So this can be a conversion factor like this. If I say that I have 8 grams of the compound, and I want to know how many grams is chlorine, then I would say, well, okay, I have 8 grams of compound. They told me that 58.64% was chlorine. And 58.64 grams out of 100 grams of the total compound is chlorine. And then from that, I can go straight from grams of compound to grams of chlorine. Now, there is the longer way that we learned last time that you can do also. And sometimes you have to do it the longer way because they might not give you enough information. But you can use mass percent as a conversion factor. Does that kind of make sense? Yeah, okay. Okay, good. So if I have compound that is X2, Y, Z3, and it is 12% Y and 22% Z, what is the percentage of X? How can I figure that out? Yeah. So what I do is I remember that the entire compound always makes 100%, right? So if I take 100% and subtract my Y and my Z, then I'm going to get whatever X is, right? Yeah, you add them and subtract them from 100. Correct. All right. So what time is it? 10:43. Oh, gosh, time goes so fast in this class. All right. So let's move to how to do, how to find empirical formula. Do their subscripts ever affect the percentage? No. Well, in a way, yes, but not really. So if I was told that I had 88% Z and like 8% Y, it doesn't really matter that I have a 2 here, a 1 here, and a 3 here, because this is going to be mass percent, and mass percent is not the same as what the subscripts are telling me. Subscripts are telling me the mole ratio, and the percentages here are telling me the mass ratio. So that's different. You're welcome. So let's take a look at empirical formula and molecular. So let's say we're looking at hydrogen peroxide. And I want to know what the empirical formula is. Well, I'm looking at the subscripts and I want to see, do they, can they be divided by the same number, whatever number that might be. So we just want to simplify it. If I was to simplify 2 over Q, what would I simplify that to be? 1, right? Right, so 2 goes into 2 one time, and 2 goes into 2 one time there. So my lowest whole number ratio would be HO. That's the empirical formula for H2O2. This is the beginning part. Like if you do some experiments in the lab, sometimes it will give you the ratio of hydrogen to oxygen, but it's not going to give you the molar mass. So you have to kind of work with what you're given from the machines to figure out what the molar mass is, or the molecular formula. The molecular formula is the empirical formula times some number n, and n is a whole number. And that's important, that n should be a whole number. Well, n doesn't necessarily have to be a whole number, because if you end up, we'll get to that part, but generally n will be a whole number. So in this case, if I took the empirical formula and I multiplied it by 2's, then I would have H2O2. That's a very basic look at how to do this. But let's get a little bit further into it so it makes a little bit more sense. All right. So So let's say, Chad, you have a question.
So with the empirical formula, you just divide the subscripts?
Yes.
Okay.
Yep, that's exactly right. Now, let's say you have, sometimes they're both the same. So with carbon monoxide, that's the empirical formula for carbon monoxide, but it's also the molecular formula for carbon monoxide. Molecular formula is the actual formula, the actual ratio. Empirical formula is the lowest whole number ratio. So if I had C2O2, its empirical formula would also be CO. So you really can't necessarily tell what you're actually going to get from this. You have to get a little bit more information. And so generally, what you're going to do, let's say, okay, so let's say we do an experiment and we're looking at water. And with our water, we do electrolysis experiment, and we break it up into its elements, hydrogen and oxygen. All right, so water, we do an experiment, and it breaks it up into pieces. All right, and that would be 0.857 grams of hydrogen and 6.86 grams of oxygen. So this is all information that my experiment tells me. That I have a decomposition reaction where I started out with water, which is H2O, and I broke it up into hydrogen and oxygen by doing an experiment. I weighed it, and I got this much hydrogen and this much oxygen. So if I want to get the empirical formula, I'm going to do, the first step is to convert everything to moles. All right, so I have 0.857 grams of hydrogen. I'm going to use the molar mass of hydrogen to convert to convert to moles. So I basically have 1 gram of hydrogen per 1 mole of hydrogen. That's from the periodic table. Technically, it's 1.007 or something like that. And so that's going to be 0.857 moles of hydrogen. Right? And then that's the next thing to do is turn oxygen into moles. It's going to be 6.86 grams of oxygen. I'm going to use the molar mass of oxygen. It's about 16 grams of oxygen per 1 mole of oxygen. This is just the molar mass. There and here, okay? Mm-hmm. And so then that's going to be 6.86 divided by 16. And that's going to give me 0.429 moles of oxygen. All right? So that's the first step. The second step is to write what's called a pseudo formula. And I'll show you what that is in just a second. Does anybody need a second on this page? Nope, everybody's good? All right, so we had 0.849 moles of hydrogen and 0.429 moles of oxygen. All right, so my pseudo formula, this is step 2. Would be to write H and then put this down here, 0.849, and O, 0.429. And obviously, I can't stop at this step. And we call it a pseudo formula, pseudo meaning false, because you have to have whole numbers when you write a formula, right? So this obviously wouldn't work. So the third step is to try to get to a whole number ratio. Um, 0.857. You know what? It might be 0.857. Is that what I wrote on the last page? Okay, we'll just change that to 857. All right. Okay, step 3 is to divide by the smallest number of moles. All right. So that's going to be, for hydrogen, it's going to be 0.849 divided by 0.429. And for oxygen, it's going to be 0.429 divided by 0.429. So that equals 1, obviously. What does this equal? $1.99. And that's close enough to 2 that we can say, well, that would be a 2. So then my formula would be H, for the empirical formula, would be H2O. These become subscripts. Of the empirical formula. All right. So those are all the steps to get to the empirical formula. And if you want the molecular formula, there's one last step. All right. So the last step is to find N. So we had H2O is our empirical formula. And let's say they don't tell us what the formula is, the molecular formula, but they just give us a mass of what we had to start with, or they give us the molar mass of the final product, right? Or, yeah. All right, so the molar mass of the compound, and then we have the empirical formula, so we could get the empirical mass. So to find N, you take the molar mass, which is going to be either the bigger number or it's going to equal it. In this case, it's going to equal it. All right, so let's say they told us that our molar mass is 18. They give us this in the question, right? So then we know the first part to find N. And then we have the empirical formula because we figured that out and all those other steps. So we can just calculate the empirical mass, because that would be hydrogen and oxygen. And total is 18 grams per mole. So empirical. That would be 18 over 18 is 1. So what do I do with this 1? This is my empirical formula. I'm going to take and multiply both of my subscripts by whatever n is. In this case, n is 1, so my empirical and molecular formula are the same. But let's look at when it's not the same. Got about three minutes. Well, if it wasn't the same, let's say you ended up with a 2, then you would just multiply by a 2 instead of a 1. So that was like an if. Now there's one last thing that I want to show you. What did I use to get the molar? That would be given in the problem. So they wouldn't, you couldn't figure out the molar mass just from experiments or just from calculations. They'd have to give you that. All right, so let's say when you figure out your empirical formula, so you take your pseudo formula, H.897, whatever, 0.31 or whatever that is, and then you figure out your empirical formula. I have no idea what it would actually be. I'm making this up as I go. So let's say I ended up with H 1.3 and O 2. Now, obviously, I can't leave it like that, right? Because this is my pseudo formula, and then when I get to my empirical formula, I get that craziness. I have to make sure they're whole numbers. So I just multiply both of them by something to get whole number. So what can you multiply 1 1/3 by in order to get a whole number? 3, right? Because 1.3 is the same as 4/3. But multiply by 3, right? So that's going to be 1.3 times 3 and 2 times 3 to be H 4 O 6. Now, in reality, this is not what I would get for an empirical formula, right? The reason I got this for an empirical formula this time was because I was making something up really fast. My guess is you'd get something more like H 1.30, and then you multiply both of them by 4, not by 4, by 3, then you would get H4O3. And this would be a reasonable empirical formula. And I know that because these are the lowest whole number ratios. So let's look at the things that you could get for a subscript. You could get something that was 1.25, 1.33, 1.5, 1.66, 1.75, or you could get like something close to 2. Generally, if it's below 1.2, I just call it a 1. Or if it's above 1.8, I'll just call it a 2. So you can round those parts. If you get something kind of in the middle, you can round it to one of these, right? So if I got 1.23, I'm just going to call that 1.25. So the numbers that I have to multiply these by in order to get whole numbers, 1.25, I'd multiply by 4. 1.33 multiplied by 3, 1.5 multiplied by 2, 1.66 multiplied by 3, and 1.75 multiplied by 4. The reason is it'd be 1 1/4, 1 1/3, 1 1/2, 1 2/3, 1 3/4. That's this number. That number. Right. So if I multiply this by 4, by 3, by 2, by 3, by 4, that's going to give me whole numbers. Okay? Oh, I've gone over by 2 minutes. All right, so that's all I have for you guys today. Homework that would normally have been due on Sunday is due tomorrow night. So don't forget about that.